So now in part B, instead of simply taking fresh air and heating it with the electrical resistance, we try to recover heat from the stale air that is removed from the workshop. So we add a new component that's a heat exchanger. In French, it's what we call the VMC double flux. In English, it's a double flow CMV in order to recover heat from the stale air. So, concerning the fresh air that is taken at the outside temperature TE, we first have this heat exchanger where this air will receive a quantity QHE of heat taken from the hot fluid, so that's the air from the workshop. So that's the hot fluid and that's the cold fluid, and this heat that will be brought will increase the temperature of the fresh air from TE to an intermediate temperature that we will call TF. And then, because we don't have a full heat recovery in this heat exchanger, we need to add supply of electrical heating in order to heat up the air up to the workshop temperature TA. So the idea here is with a given design of heat exchanger to calculate first the overall heat transfer coefficient in order to estimate the heat flux that is exchanged in the heat exchanger, and with that we can calculate this intermediate temperature and how much heat supply we need to add with this electrical heating. So we have a description about the sizing and the dimensions of this double flow CMV. So it's a heat exchanger that is quite simple. It's made of many plastic tubes. So the flow of stale air is divided into a set of 100 tubes. So the stale air is going through the tubes and the fresh air is coming in contact flow around the tubes. These tubes are made of plastic, so plastic has a low conductivity, but they are very thin. The diameter of the tubes is 3 centimeters and the thickness of the plastic is 0.3 millimeters. And we know that the length of this whole heat exchanger is 10 meters, so that's a very long heat exchanger. So, in order to calculate the efficiency of this heat exchanger, we need to understand what's going on. So here we have a heat transfer from the hot fluid, so the air that is coming from the workshop, the stale air. This heat flux QHE is going through 3 thermal resistance in series until the fresh air that is coming on the opposite side. We have the internal convection with this internal convective resistance with A, the heat transfer area between the fluid, and H index I for the internal heat transfer coefficient. This heat transfer area between the hot and the cold fluid is the same, or can be considered the same at the internal part of the tubes and on the external side. This is due to the fact that the thickness of the tubes can be taken as negligible compared to the diameter of the tubes. So we can consider that the tubes are very thin, and we can neglect the difference of area between the internal and external area of the tubes. Of course, here we talk about the total heat transfer area between both fluids, so we need to take into account all of the tubes in the calculation of this A. Then we have the conduction through the plastic in order to transfer heat from the internal part to the external part of the system. This conductive heat transfer can be, in this case, written as a 1D heat transfer instead of a radial heat transfer, and this approximation is true because we consider that the tubes are very thin. You can also do it with the logarithm and the expression of radial conductive thermal resistance, and you will get the same results more or less. This conduction could usually be negligible and neglected when we consider that the thickness is very thin, like in our case. But here we have something special, it's that the tubes are in plastic and they have also a very low conductivity. So E is very small, but lambda is also very small, so we cannot neglect a priori the conduction resistance, and it's better to keep it in the calculation, and then we can see later if this resistance is negligible compared to the other ones. And then we have the outer convection resistance, and once again it has the same expression than inside, but here we need to consider the outer heat transfer coefficient.